Finally today, I want to go over the power of this equation and what it means that velocity is squared in a very important thing in real world, and that is, of course, in football. And in football, there is a position called a safety. And the safeties are the ones who are defensive backs. They sit back and see the ball coming so they can get a full head of steam and hit someone at full speed. And so I have come up with some data, this is actual data from the internet here, that over the last 40 years, in 1970, 80, 90, 2000, and 2010, what did the average safety who came into the NFL, what did he weigh? And what was his time in the 40-yard dash, which is a proxy for how fast he is. So the weight is going to give us our mass, and then how fast he is in the 40-yard dash will give us our velocity squared. And what you see when you interpret this data is that over the last 40 years, people just haven't gotten that much bigger as a safety. In 1970, they were 188 pounds, and now 40 years later, they're 198 pounds. They've gone up 5.3%. It's a pretty big jump, but not a dramatic jump compared to how much faster people have gotten over the last 40 years. Over the last 40 years, their time has gone from 4.85 on average to 4.35. Let me just tell you, 4.85, that guy's fast. Seriously fast. 4.35 is jaw-dropping fast. And in that time, they've improved over 10%. But it's not just 10%, it's 10% squared in terms of how much kinetic energy, which is how much force they can deliver when they hit somebody. So the combination of a 5% increase in mass plus a 10% increase squared means that today people are hitting at 128% as powerful or as forceful as they were in 1970. So that brings up a question. If I own a team, or if I'm the general manager of a team, I have an incentive. Another one of our words of the week, incentive, to draft the best players I can. I want to draft the players who I think are the best players who are going to help my team. The problem is that over the last 40 years, as people have gotten bigger and more importantly have gotten much faster, the amount of force that the safeties can deliver has gone up so dramatically that safeties can't last as long as they used to. That safeties, even though they're the hammer hitting the nail, eventually that hammer gets hit one too many times and gets injured. And so safety careers aren't as long and they don't play as long. And so as a GM, as a general manager who's trying to put together a football team, I have an incentive problem. I want the best players I can, and I know that safeties are important, and the faster they get and the more they weigh, the better they'll play, but also the harder they're hit and the shorter their career is going to last. They're going to get injured. And that's what today's Math Extra Credit reading is about. Peter King, who is a famous writer of football, who works for Sports Illustrated, he wrote an article about this in 2010, so last year, about this, and the URL is on our class website, so you don't worry about copying it down now. But he has an article that talks about the incentive problem that GMs have in trying to draft safeties, because believe me, they know this information very well, and they really understand that kinetic energy, what that means in football.